All right. All right. Cool. All right, let's go ahead and get into today. Hello, everybody. Welcome back to the stream. Hope you're having a good day today. My name is Michael. I'm a little bit later than normal, but that's okay. What's good? Today we're going to be finishing up MIT OpenCourseWare 6.00002 problem set 4. We have a couple more problems left of this overall problem set, so it shouldn't take us too long. I didn't realize, I forgot that it's been so long, you guys, I forgot that we did the first half already. I completely forgot. So we have to do this the second half, which hopefully won't be that bad. So thank you guys so much for joining me today. Let's go ahead and get into the coding. Again, this is MIT OpenCourseWare 6.00002. You can find information online if you just look up OpenCourseWare for MIT. It's a course that they offer for free online, and we're taking it here. All right, let's go ahead and get started. Cool. Okay, so last time we left off, we created some, we ran a simulation without antibiotic here. Right, and we were able to get this curve, which resembled what they had as well. Right? So, that being said, we're on problem 3 here, I think, now. Cool. Okay, we're on problem 3. Hey, how's it going, Zero? Yeah, this course kind of eventually leads into machine learning, and then we'll be taking some more machine learning courses after this. But yeah, let's go ahead and keep going here with problem number 3. Calculating a confidence interval. Using data collected in the simulation from problem 2 as our sample, we want to construct a 95% confidence interval of an estimate of the average bacteria population at certain time step 0 indexed. Given data x index I for I, 1, 2, all the way to n, some formulas you might find useful are the mean formula, standard deviation, standard error, 95% confidence interval. Okay. So let's go ahead and do this. Using the sample data collected from running the call to simulation without antibiotic providing pset4.py, compute the record and record the 95% confidence interval for the population estimate at the time step 299 in your write-up of ps4writeup.pdf. Okay, so it wants the time step 299. So find the standard deviation of populations across different trials. You may not use any third-party functions to calculate standard deviation, such as NumPy standard. Okay, cool. So this one's just the standard deviation given populations. Okay, so we're going to do these just one at a time. Nice. Not that bad. Okay, let's go ahead and implement the standard deviation function. This is fun. So we have populations. So finds the standard deviation of populations across different trials at time step t by calculating the average population at time step t. Compute average squared distance of the data points from the average and take its square root. Okay, so populations is not, doesn't mean types. So this is populations here, which is what's returned from simulation without antibiotic, which is this. Which is all of our run values. Resolution. Make plot curve. Oh. Just gonna get caught up on what we wrote last time. It's been like a month. So make one curve plot. Takes in the x coordinates, which is a list. And the y coordinates is y values. Calculate population average. Oh, my headphones died. No. Okay. Let's think here. So using data collected in your simulation from problem set 2. So obviously the resolution values, which we aren't even, but the y values are what we're using as the resolution, and we're pending calculating average pop given the populations in some trial for trial. So population is a list of lists of two populations. Okay, so hold on. So populations is a 2D array. The number of bacteria in trial I at time step j. It's the number of bacteria in trial 1. Okay, got you. So number of bacteria. So every row is a trial, and j is a time step within said trial. Okay, so we have populations here, which is that 2D array, right? Across different trials at time step t. Okay, got you. Cool, so let's just make a note saying that populations is a 2D matrix where each list row is a trial and each index is each value in the row is a, what was it again? Number of bacteria at the time step j. Okay, so, sorry, hold up. Keep getting lost. Yeah, so the population is a 2D matrix where each list or row is a trial, and each index within in said row is, right, which is a column, is a time step. The value at the index, at the time step index is the number of bacteria. Okay, cool. Hey, what's up, Paul? How's it going? Yeah, I had to think back. We solved the first part of this problem over a month ago. So it's literally like, oh my gosh, we were slacking on this course for a while. We're back on it though. We're back. So I had to relearn what we did last time. I had to go back and relearn what the parameters were. Okay. And then we have a time step t. Okay, this is pretty simple. So what we're going to do is to compute standard deviation, we have to calculate the average population at the time step and then compute the average square distance of the data points from the average and take its square root. Okay, so we need to take the average of the entire time step. So n is equal to the length of populations yeah, right? Because the length of the number of trials, you're going to have one time step for every trial. So n is the length of populations, right? Or the length of rows, which is equivalent to the number of time steps. No, the number of time steps is the length of populations, let's say index 0, because it would be one of the singular rows, not the length of all of the rows. No, that would be the number of, we don't want the number of time steps. No, we want the length of populations because we don't want the length of the time steps. We don't care about the number of time steps. We want the how many trials there were because that corresponds to one time step per trial at that. You can't have like a duplicate two time steps. You have a single two time step in that trial, and the next trial you have a two time step, and so on and so forth. Right, so n is the length of population. So we'll say this is the number of trials, which represents number of which is the number of or count of the like it's not the time steps, but the like singular time step t or number of trials. I don't know. Like, oh, that's the best way I can think about naming it. Okay, so we have the number of trials here for this problem. And then so we're going to compute an average. So we need to do a sum. So let's do, I'm just going to make a dummy variable. I'll rename it in a second. Don't mind me. So we want to sum an array of row index of t for row in populations. Am I tripping? Row for row. I've been writing in C too much. I haven't. This is what happens when you go and start writing in C and do stuff in C. Am I tripping? Row. Dude, am I really about to have to look up a list conf example? How long I've been doing this? Yeah, row index t for row in populations. If row, no, it does not like the sum. Okay, yeah, it doesn't like the sum. Oh, sorry, it's the sum function. I'm tripping, man. Yeah, I write in Python. That's for sure. I've been doing this for a year and a half. Okay. Sorry. I'm warming up here, you guys. It's been a long day. Okay. So we have, we're going to sum we're going to take a sum of all the values at that row index of t for every row in the population. So this will give me the total sum at t. And then what we'll do is we need to compute, well, we actually have this function, calc population average at n. Oh, I'm tripping. Dang it. Self dot, or so we'll call calc pop average given populations and t. Dang it. That would have been easier. I already wrote this function. Okay, and then what we're going to do is write this standard deviation. So now that we have the average, we're going to say for row in populations, we're going to go to row index of t, and then what we're going to do is we're going to compute a distance of the row of t from the average, right? And then we're going to call this this is going to be called the distance, right? And then we're going to do this. Yeah, we're going to do this, sorry, times power of 2 and call this square distance, right? And then we want to sum all of these square distances. Okay, so we're going to sum all of the square distances. So we'll say square distance sum is equal to 0. And then we're going to do square distance sum plus equals to, and I guess we'll just put this here. Right? So that'll give us the square distance, and then we're summing all of those for all the values. Then we're going to take this and multiply it by, 1 over n root math dot square root 1 over n, which is the average which is the length of populations. So 1 over n times the square distance sum. Yeah, right? And then this will give us the standard deviation. And then we want to return. So this returns a float, the standard deviation populations across the different trials. Okay, so then return standard deviation here. Now, hold on, I'll catch up in chat in 1 second. Okay, so cool. So what we're doing is we are having to loop through, right? This kind of symbol, when you see this symbol like for all the values of indexes, kind of think of like looping through and getting you're summing, right? So you have to loop through and sum. Now, I probably could have done like whatever this in a list comprehension, but it's whatever. It's a little bit cleaner this way. So for every row in the populations, we're going to go to the value that we're looking for and take that less than the average, like right here, right? And then we're going to square that entire sequence like this, right? And we're going to then add it to that summation that's happening from 1 to n. Now it's one indexed in this example, but it's 0 indexed in our code here, so keep that in mind. And then we're going to take the square root using math.square root of, it says we can't use any built-in functions. They're not calculated. That does standard deviation. Cool. So we can use standard square root. Or we could raise this to the power of what? 1/2? Is that what you have to do? Or is that the opposite? I can't remember, dude. It's been a while. I'm trolling. Okay, so then we take 1 over n, this guy here, and multiply it by that square distance sum that we got. And so that'll return the standard deviation. So let's see what happens. We have PyTests here. Oh, so this is just our testing data. So let me call then no, hold on. Let's call, we want to call this guy, and we have populations here. So now we can call print population, what is this called? Calc population standard of the populations that we have currently on hand. So if we run this guy, uh-oh, we got anything here? Now if we exit out of this, oh, we need to give a t. What t do we want to use? We want to use 299. Let's run it. It's a little slow. Okay, ready? Watch right here. Let's see. All right, we got a standard deviation of 16.2697776. Okay, so we got something there. And if that's correct, I don't know. I wish it gave us like a... Oh, here's our
You're
test.
not that guy, pal. Trust me. You're not that guy.
Hey, who's that?
You?
Who is that?
Absolutely.
Who's not that guy, pal? Hey, Pavan, thank you so much for the follow on YouTube. Appreciate you so much. Let me go ahead and get the tunes back going here. My AirPods charged back up. Okay, let me catch up on chats. I've been away on chats. Hey, Hall Minotaur, welcome. Yeah, we're cooking, my boy. I appreciate the kind words. Lance, how's it going? Hey, Kyrim, welcome back in. Hey, Lance. Explained very well, man. Being able to talk to code like this is rarely. I see. Nice. I appreciate the kind words. You're always hyping me up. How you doing, Kyrim? It sounds like that Pokemon, that legendary one. Hey, what's up, Michael? How have you been doing? Haven't seen you on stream for a while. Have a lot of schoolwork. Oh, what's going on, Stoic Mindset? How's your school been? Are you in CS? Welcome back in. Try hard casual. How do you learn fast? Just showing up every day, my guy. Honestly, I've kind of learned a little bit quickly, like throughout my entire life. Just pick things up naturally, like just I don't know. I've kind of always had that ability, but definitely showing up every day helps compound it for sure. He just installed an AI with himself. Mike got that brain chip. Hey, Red One, I suck at coding. What do you recommend? Do these problems with me. These are the introduction. These are, like freshman, sophomore level problems for MIT courses that are offered at MIT. We are doing these courses and working our way through a lot of these collegiate level books and courses and stuff. So now if you're wanting to get better at coding and you found inspiration through what I'm doing, not saying that I'm doing anything right at all, like I'm learning myself. Let me move that the Twitch. But I know we have found some success in our our coding so far. Where can I put this? It's not like gonna be like so. Oh gosh. Let me properties. Let me add some CSS to this. Dot body. Look at me, dude. And let's do background black. Okay. No. Background dash color. That didn't work either. Gosh dang it. Oh, it's not dot body, it's just regular body. No. Let's try one more time here with like hey, look at that. Okay, let's see it today. Hello. Does it pop up? Yeah, let's go. Look at us, CSS over here, front end boys. Let's go. Yo, show your front ends, boys. Let's go. Show your front ends. Pause. 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 Show your front ends. Oh my gosh. Cool. All right, I just added a little CSS to that our chat box, and then what I'll do is actually I'll throw it over to the top right again. Here we go. It's been hard as a freshman. I've been doing Coursera CS courses right now. Oh, nice. To be honest, I've been just getting my feet wet in Python again. Gonna do the Python MIT course and do some other Coursera. Nice. Yes, do this one with me. This is a great one to do with me here. Pause. Okay, here we go. Let's keep pushing. All right, so let's run this test and see what happens. Okay, so unit test no attribute make sweet. Ah, I hate how it does this. Okay, this is the population. So what if I import this population and use this as my population? So what am I using as population here? The number of bacteria. Okay, so this is giving the populations back to us. So if I just use this population instead, right? So let me go like this. From PS4 tests, import population. And then let me go down here. I'll comment out this guy. And then let's put the population in here. And let's see if we get that standard deviation from that assertion. Cannot be import name population project in a piece of a test. Likely due to circular import. Oh shoot. Let's just say it's from my current directory. Like my current root directory. Now we need to do under init here. No. I suck. Let me just do this then, whatever. Let me go to my tests. Let me take the population here. And we'll just throw it at the top here. And then we will, now if I run this, 10.735. Yes, let's go. Let's go. We did that one right. Let's go. Let's go, let's go. Okay. Hyped. That's cool. All right, cool. Let's go ahead. So what I did there was I just used that population from our test because this was written when some of these modules are a little outdated when they were written, these tests. And so some of these modules don't have these methods anymore. And so what I did is this is that assertion, and it's asserting this standard deviation. And so I checked it, and I checked for the same population on against our function, and it worked. So nice. It's the same number basically. Okay, cool. Let's keep pushing here. That solves that one. Okay, so now what we're going to do is this calc 95 confidence interval. So finds the 95% confidence interval. Finds the 95% confidence interval around the average bacteria population at time t by computing the mean and the standard deviation of the sample, using the standard deviation of the sample to estimate the standard error, using the standard error of the mean to construct confidence intervals around the sample mean. Cool. So this is pretty simple given all of our functions up to this point makes this really, really easy. It's trying to really show you that, trying to build these out, these functions, and then use them all together. So we can just call calc population standard for the populations, and then we're going to call this standard dev here, and then what we will do is we're going to compute the standard deviation over the square root of n. So n is equal to the length of populations, and then we're going to compute math.square root on the standard deviation over n. Oh, sorry, no. Not math dot, we're going to do the standard deviation over math dot square root on n here. And then what we're going to do, this is called the SEM, standard error mean. And then what we will do is take our average. Our average is equal to calculate the population average given the populations. And then what we're going to do is compute the confidence interval 95 is equal to our average. how do we write this? A range object returns a mean, float the sample mean with a tuple. 9.96 times. Okay. Oh, okay, got you. It doesn't even want us to do that. So we will do this. Return a tuple of the average and the standard deviation. No, sorry. The sem times 1.96. Okay, let's run this. Calc the 95 confidence interval given the population. And let's see what this should give us. We want to assert here. So 6.65. Always forgetting T over here, boys. 6.65. Oh, I'm trolling. Oh, we want to do 299. Oh, we're not printing. All right, let's print. Let's go. 6.65. Let's go. Nice. I am hyped about that. Let's go. All right, cool. So we are successfully computing both the standard deviation from scratch and the 95 confidence interval by computing the standard error of the mean and taking that and multiplying it by 1.96. Cool. All right. Now we can comment out that one. That solves problem 3. Hey, Pew Pee, how's it going? I saw you learn in C. Yeah, we've been diving into C. We've been getting some good practice problems and whatnot and learning more. I'm hoping to learn a few more fundamentals and more about memory, and then I can start to maybe write my own projects and scripts and see what we can start to make. So, yeah. Thank you so much for coming in today. Welcome, welcome, welcome. All right, let's do number 4. Problem 4. All right. Implementing a simulation with an antibiotic. In this problem, we consider the effects of both administering an antibiotic to the patient and the ability of the bacteria cell to inherit or mutate genetic traits that provide antibiotic resistance. As the bacteria population reproduces, mutations will occur in the bacteria offspring. Some bacteria cells gain favorable mutations like antibiotic resistance. Note that bacteria in lower population densities mutate at a faster rate. Resistant bacteria class. Resistant bacteria is a subclass of simple bacteria, which has the potential to gain antibiotic resistance through a mutation. The scientists on the 6.0002 staff have found that bacteria that develop antibiotic resistance also seems to gain other mutations that cause a different death rate. If a resistant bacteria gains antibiotic resistance, it will die with the given death probability. Resistant bacteria that do not have antibiotic resistance will die with a death probability divided by 4. Whether or not the bacteria have this mutation is determined at birth. Okay, cool. Pretty easy. Implement the resistant bacteria class according to the doc strings and description provided above. The methods you need to implement are init, get restraint, resistant, get is killed, and reproduce. Alright, cool. So we have self dot, and we'll copy this down 4 times. We have birth prob equal to birth prob. So the birth probability is a float, either 0 or 1. For reproduction probability, for a float in the range of 0 to 1. And then self.death prob is equal to death prob. Self dot resistance, Boolean whether this bacteria has antibiotic resistance. Resistant equals to resistant, and then self dot mutation probability is equal to mutation probability, which is a float mutation probability for this bacteria cell. This is the maximum probability the offspring acquires antibiotic resistance. Okay, so get resistance returns whether the bacteria has antibiotic resistance or not. Okay, really simple. Return self dot resistance. So that's a Boolean, so it'll return true or false. Is killed stochastically determines whether this bacteria cell is killed in the patient's body at a given time step. Stochastically determines whether this bacteria cell is killed in a patient's body at a given time step. Checks whether the bacteria has antibiotic resistance. If resistant, the bacteria dies with the regular death probability. Okay. Checks whether the bacteria has antibiotic resistance. Okay. If resistant, the bacteria dies with the regular. If not, the bacteria dies with the regular divided by 4. Okay, if self dot resistant. Why would I have like self get resistant here when I can just refer to self to my individual variable? I mean, maybe it's best. Maybe it wants me to abstract these into like prefixed hyphen or underscored variables, which is Python slang for do not mess with this, and then calling it with a getter. But I'm not calling any other getter in the entire thing, so like I don't know, it's kind of silly. Whatever. If self.resistant, right, if it is resistant, we're going to decide whether it has dies with the death probability. So checks whether the bacteria has antibiotic resistance. If it is resistant, the bacteria dies with the regular death probability. If not resistant, the bacteria dies with the regular death probability divided by 4. Returns true if the bacteria dies with the appropriate probability, and otherwise false. Okay, so we'll have to declare a variable here called chance, which will be a random variable, which will provide us a random number between I think random.random just returns us a singular value, right? Of 0, between 0 and 1. Yeah, perfect. Okay. So here's our chance. And then what we're going to do is say that, so the probability that it dies. I'm confused. Am I checking? So I'm checking if it is killed here. Right? So check whether the bacteria has antibiotic resistance. If it is resistant, oh, okay, got you. So if resistant, we're going to check here if our chance is within the death probability. If chance less than or equal to the self.death probability, then we're going to return true. Right, and then what we'll say is else we're going to return false here. Now what we'll say out here is if there is not antibiotic resistance, we have a basically this same phrase, but death probability is divided by 4. So if our chance is within the boundary of that overall probability, so let's say there's an 80% chance that this bacteria dies when called upon, right? So if we call this function on the bacteria and it has a 0.8 death probability, then what if we roll a random dice or roll a random number between 0 and 1 and it lands within 80%, then it will die, right? You have 80% success rate of death for this. Now, if you aren't resistant, you divide it by 4. Right? But why am I dividing this value by 4? That would make my chance even harder if it is not antibiotic resistant. Resistant bacteria that do not have antibiotic resistance will die with the probability of the death probability divided by 4. If we take our death probability of, let's say, 20% and divide it by 4, our death probability only becomes like 5%. Right? What's up, Jimmy Boats? Hey, Sen, how's it going? I appreciate you coming in. Hold on, I'm gonna do this. Why is the death prob divided by 4 for non-resistant? I thought it would be increased to be more resistant. No, to be less resistant. If the death prob is 20% and it is not resistant, the death prob is now 5%, which is way less likely to die. If bacteria is not resistant, you should logically be more likely to die when exposed to antibiotic, not less likely. So a non-resistant, why might it be divided by, there are two-part typo. Resistant bacteria might have a cost of resistance. Oh. Oh. Hold on, I thought I read something where it said some bacteria in lower population densities mutate faster rate. Resistant bacteria might have a cost of resistance. What? Why would it do this? If a bacteria gains antibiotic resistance, it will die with the given probability. Bacteria that do not have antibiotic resistance will die with probability divided by 4. Okay, I guess. If there is resistance, you check the chance. So we'll set result to equal false. We'll set result equals to true. Else we're just going to return result. So if the bacteria is resistant and the chance is within the death probability, then we're going to return true that this bacteria dies. Set resistance to true and then return true. Else, so then I think I can remove this actually and just set this out front. Right, I think that might take care of it. So if there's resistance, and if the chance is less than or equal to the death probability, then we set res to true. Else, if there is a resistance and chance is within the death probability divided by 4, we'll set res to true. Return res. Why are my headphones dying again, dude? Are you serious? Come on. Come on, man. It's my charger. Where's this thing at? Clearly didn't charge very much. Where did it go? Boy, oh boy. I thought I had a charger. Like an actual USB-C, but I guess I'll have to use the wireless one. Whatever. Alright. Cool. Hey, what's going on, Sir Drippy? Sir Drippy. Yeah, yeah. Okay. Okay, cool. So reproduce. Stochastically determine whether this bacteria cell reproduces at the time step, called by the update method in the treated patient class. A surviving bacteria cell will reproduce with probability of the birth probability times 1 minus the population density. If the bacteria cell reproduces, then reproduce creates and returns an instance of the offspring resistance bacteria and will have the same birth, death probability, mutation probability values as its parent. If the bacteria has antibiotic resistance, the offspring will also be resistant. If the bacteria does not have antibiotic resistance, its offspring will have a probability of self-mutation probability times 1 minus population distance of developing that resistant trait. That is, bacteria's less densely populated environments. Okay, this one's a little bit more tricky. So reproduce, we have a population density given to us, and this method is given to a bacteria cell. So we're going to call, this is going to say if it's called, this is going to be called, right? And so we'll say repo prob is going to equal to the self.birthprob times 1 less than the population density provided, right? So that'll give us the repo population or probability. Okay, then we're going to say chance is equal to random dot random, and we're going to say if chance is less than or equal to our repo probability, right? If the bacteria cell reproduces, then reproduce creates and returns an instance of the resistance bacteria class. Okay, so we're going to say child is equal to resistant bacteria, and birth prob is going to be equal to self dot birth probability. Death probability is going to be equal to self dot death probability resistant. So we have to do something with this one, right? And then and mutation probability. Right. So death, resistant. So those 4 attributes. 1, 2, 3, and 4. Perfect. Okay. But what we need to do is we have to determine a few more conditionals here. So if the bacteria cell reproduces, then it returns an instance of the offspring, which will have the same birth probability and mutation, birth, death, and mutation probability. If the bacteria has antibiotic resistance, so we'll have to say if self dot resistant. So if we are resistant, Then we're going to set child resistance equals to true. And we'll come out here and set child resistance equal to false out front here. And then we'll set it to true here. And we'll set child resistance equal to this. Okay? And then what we'll say, so what will happen is if the chance is within the probability, then we are going to flag the child resistance as immediately false. We're going to say if there is resistance to the parent that we're currently on, then we're going to override the child resistance to true, so that when we come out of this if conditional and create the child, we set the child resistance, whether it be false or override it to true, as that resistance. Now, let's see what else it says here. If the bacteria has antibiotic resistance, the offspring will also be resistant. If the bacteria does not have antibiotic resistance, its offspring will have a probability. Okay, so we'll say child resistance is equal to, what we'll do is this. We can literally just copy this and set our default to this. No, sorry. We want to keep that as false. We're going to say if there isn't any resistance, then we're going to say resistance chance is equal to this. And then what we're going to do is say, we'll say this is resistance probability, right? And then we'll say, we'll call this repo chance, reproduction chance. And then the resistance probability, so we're going to call resistance chance is equal to random here. And then we're going to say if resistance chance less than or equal to the resistance probability, then we're going to, if the resistance chance is less than or equal to the resistance probability, meaning that you randomly bred this, even though your parent didn't have it, you randomly did end up getting it. Self dot, or say child resistance is equal to true. And then we'll create the child out here, and then we will okay, so then we'll create the child, and we will return the child. Else raise a no child exception. So this if block will always hit this return for a child, so we don't even really need this else, right? Okay, so what's happening here is we're getting a random reproduction chance, right? We are then determining a probability for reproduction. We are then determining if the reproduction chance is within that reproduction probability. If it is, we know we're going to produce a child, so we enter this section here. We set the child resistance to false. If the parent is resistant, then the child resistance becomes true. Else, we get a random resistance chance, and then we calculate the resistance probability of the child. If the resistance chance of the child is within the scope of the resistance probability of the child, then the resistance of the child becomes true. And if that doesn't happen still, the resistance remains false, and no matter what, the child is created within this scope, and the resistance is set as the child resistance, and we return the child. Cool. So if I look at our test here, there's no test for this one, so okay, whatever. But I think that is the gist of it. Okay. Wow, this one's longer than I thought. Treated patient class. The treated patient class is a subclass of patient and represents a patient with antibiotic treatment and manages a collection of resistant bacteria instances. The treated patient must make use of the new methods in the resistant bacteria and maintain whether the antibiotic is administered to the patient. The antibiotic is given to the patient using the treated patient class, set on antibiotic method. If the patient is on the antibiotic, then only bacteria cells that have resistance will survive. Bacteria cells with resistance to the antibiotic continue to reproduce normally. Okay, so now we're going to implement the treated patient class here. Represents a treated patient. The patient is able to take an antibiotic of his or her bacteria population and acquire antibiotic resistance. The patient cannot go off the antibiotic once on it. So bacteria is a list representing the bacteria population, a list of bacteria instances. So self.bacteria is equal to bacteria. We have max population is the max population for this patient of bacteria, which is an integer. So self.maxpop is equal to maxpop. We then have set antibiotic, which will go ahead and administer an antibiotic to this patient. The antibiotic acts on the bacteria population for all subsequent time steps. Okay, so the minute set on antibiotic. What is this? Administer an antibiotic to the patient. The antibiotic acts on the bacteria population for all subsequent time steps. What? Get the population size of bacteria cells with antibiotic resistance. Returns int the number of bacteria with antibiotic resistance. Okay, so we'll say we'll say length of val for val, or we'll say bacteria for every bacteria in self.bacteria if bacteria dot if bacteria dot resistance. Right? and then we're going to return this. You don't say pass, no. Okay, so that'll return the number of bacteria in the current object that have resistance. So update the state of bacteria population in this patient for a single time step. Update should execute these actions in order. Determine whether each bacteria cell dies according to the is-kill method, and create a new list of surviving bacteria cells. Okay, so survivors is equal to an empty list. And we're going to say for bacteria in self.bacteria, we're going to say if so is killed returns a boolean, true or false, if the bacteria dies or not. Okay, so if bacteria dot is killed, then what we're going to do is, or if not, then we're going to survivors append the bacteria and create a new list of surviving bacteria cells. If the patient is on antibiotics, the surviving cell this function should initialize self on. Oh, got you. Here we go. Hey Kyrim, how's it going? This function should initialize self.on antibiotic, which represents whether or not. So we're going to create a self on antibiotic. We're going to set that equal to false, probably. Yeah. Don't forget to call the patient's init method. Oh, yeah. We're going to super init args. Okay. Yeah, just like that. So we call that guy. What does the simple bacteria have? A birth probably and death probability. It's killed. So then my resistant bacteria takes in simple bacteria but also has these already. Okay. So you don't actually, okay, got you. So we init the patient information and we set self on antibiotic to false. Okay, so then this, we administer the patient, so we say self dot on antibiotic equals to true here. Cool, pretty simple. If I would read the problem, wouldn't get stuck, right? Okay, cool. So we've done number one. If the patient is on antibiotics, the surviving bacteria cells from one only survive if they are resistant. Okay, so then we'll say Um, so we're looping through the bacteria. If okay, so then we would say for bacteria in survivors. Well, actually, we would only want to keep the survivors. So if bacteria is not killed, um, if self dot um, on antibiotic and self dot if self dot resistant, if self dot antibiotic and bacteria dot resistant, we're going to append survivors here. Elif if you're not on antibiotic, if you're not on antibiotic, then you just append the survivors. If you're not on antibiotic, you append the survivors. If you're on antibiotic resistance and the bacteria is resistant, then you're going to append. If you're on antibiotics and the bacteria is not resistant, you're going to continue. If you're not on antibiotic resistance, if so we'll say if self dot if not self dot on antibiotic survivors dot append bacteria. Elif if you're not on antibiotics, then you append the bacteria. If you're on antibiotics and there's resistance, you also append the bacteria. Else, you are on antibiotics and the bacteria does not have resistance, you would pass, you would continue. So nothing there. Okay, so that would calculate that. So then we're going to say population density is equal to self dot get total population, right? Patient like a total pop. Okay, cool. So then here. Based on this value of population density, determine whether each surviving bacteria cell should reproduce and add offspring bacteria. Based on this value of population density, determine whether each surviving bacteria cell should reproduce and add offspring bacteria. Okay, so we'll say offspring is equal to an empty list. And we're going to call for bacteria in survivors, we're going to call bacteria dot reproduce, and bacteria dot reproduce has population density given to it. Right, this will return to us a child object. So try this except for a no child exception. We're going to continue. And then this is going to give you back a child. And we're going to call offspring.append that child. And then we're going to do survivors plus equals to offspring to combine the list together. And then we're going to do self.bacteria is equal to survivors. And then we're going to return self.get total population. So we have a list of survivors for every bacteria that's currently in our bacteria population. If the bacteria is not killed, then what we're going to do is check if I'm currently on antibiotics, the patient's on antibiotics. If they are not on antibiotics, then the bacteria just gets added. If they are on antibiotics and the bacteria is resistant, then the bacteria gets added as well. Any other case, they don't get added, where the bacteria would be off antibiotics. That's here. If so if it's on and this one isn't on, then isn't resistant, then it would pass. Now we have offspring, so we get the population density, and then we call for every bacteria we determine whether that bacteria reproduces or not, and returns us back an offspring, and we append that value to the offspring list, except if there's no child, right, because of this reproduce, then we continue over this bacteria. And then we add the offspring to the survivors, and then set, and then return this thing. Okay. Oh, population density is... We might have something wrong in our patient class. Hold on. So current bacteria population divided by the maximum population. Okay, so the population density dividing the current bacteria population by the maximum population, and we have self.maxpop is here. Okay, so, and that's the population density here. So I'm going to take this, go down to my guy down here, and say that the population density is equal to length of survivors divided by self.maxpop. Yeah. Right. If bacteria is killed. If not, bacteria is killed. If not, antibiotics or bacteria resistance. Oh, so you can say if not self.antibiotics resistance or bacteria resistance, then you append. Okay, so let me take my new function here. I think that that'll probably do it. You can make the reproduction loop a little cleaner by doing this. For bacterium survivors, try it wants us to pass. Just handle it silently and pass. Okay, sweet. Hey yo, how's it going? Welcome, son. Appreciate you. Hey, Abukir. I appreciate you coming. Yeah, we're doing the MIT Open course. We're 6.0002 class right now. We are on the problem set 4, close to week 9. After we finish this one, we'll watch the week 9 lecture probably either tomorrow or the next day. Okay, cool. That is that function there. So this is resistance population. So I'm gonna give it this function too and see what it likes, if it likes this one. Perfect again, perfect. Nice. Okay, nice. So now problem 5, lastly. In this problem, we will use the implementation you filled in for problem 4 to run the simulation. The simulation explores the effects of resistant bacteria and antibiotic treatment. Implement the function simulation with antibiotic according to the behavior described in the docstring with the provided code. Use the provided helper function make two curve plot to generate the plot of your results at the end of your simulation with antibiotic function. The plot should have the following two curves: the average population bacteria size over time, the average population size of antibiotic resistance bacteria over population over time. Run the two calls, simulation A and B, simulation with antibiotic that we solved in PSET 4. Paste copies of the two graphs created in simulation with our parameters into your write-up. Okay. No, you definitely can do it. This is not that bad. This is pretty easy. It's just take a little bit of time to to go through all their stuff. Um, okay, simulation with antibiotic. Okay, so now we need to run simulations and plot graphs for problem 4 for each of the number of trials. Okay, so we're going to say for trial in trials in the range length of trials. Num trials. Right? So we're going to loop over the trials. We're going to instantiate a list of resistant bacteria. So bacteria is equal to a list where we have resistant bacteria. Birth prob equals to the birth prob. Death probability equals to the death probability given. The resistant equals to resistant. And mutation probability equals to mutation probability. And we're going to multiply this by the num bacteria. Right? I don't think we can actually do that because I think it references the same object. Like that. Okay, so we're going to create a list of bacteria, resistant bacteria for every value in the range of number of bacteria. We are going to run a simulation for 150 time steps and add the antibiotic. Run the simulation for 150 time steps. Add the antibiotic and run the simulation for an additional 250 time steps. Okay, so total bacteria equals to a list, and resistant bacteria equals to a list. We'll say counts. Right? So we're going to run the simulation, right? Run the simulation for 150 time steps. I'm getting kind of tired, you guys. I might have to call it. We might have to do a part three, unfortunately. I didn't want to do a part three, but I'm losing steam here, you guys. So we're going to run a simulation for 150 steps. Okay, so we're going to call no simulation without antibiotic. We're going to run the simulation. So this is going to run the simulation. Run the two calls, simulation A and simulation B, to your simulation with antibiotic that we provided. Shoot. How do we run the simulation? Is this it's 95% confidence interval? Calc standard deviation. Simulation with antibiotic. Without. Population average. Patient class. Bacteria. Make two plots. Make one plot. Okay, so I think we run the simulation. So this goes simulate changes in the bacteria. Okay, so if we create a new patient, right, we create a new patient, we give bacteria equals to bacteria, to max population equals to max pop. Okay, and now we have a new patient object. So what we're going to do is run it for 150 steps. So for in range I in, we're going to do it in a total of 150 plus 250, 300 steps, right? If I is less than or equal to 150, we're going to okay, so then we're going to call new patient dot Guess the size of current bacteria population. The current population. So we say, I don't even know. We say new patient. Oh, we say new. So we say patient dot update. We call the update function. The update function returns us the tuple of oh yeah, so this is just a singular patient. Right, this is just a singular patient that returns the total population. And the number of resistant bacteria is 0 because this patient is not treated. So we'll say um, this is equal to the number bacteria. And we're going to call total bacteria counts dot append the number of bacteria. We're going to call resistant bacteria counts dot append 0. And then else, right, what we're going to call so that goes there. If this, we're going to treat the patient now. Oh, hold on. No, we'll keep the patient out here. Then we'll say else. Okay, no, we'll just do this for 150 runs. Right? And then what we'll do is say for in range of 250, we're going to of 250, what we're going to do is call, we're going to make a new patient equals to treated patient on untreated patient. Called treated patient. And we're going to create a treated patient. We're going to call bacteria equals to untreated patient dot bacteria, and the max pop equals to max. Max pop. Right? And then what we're going to do is call number of bacteria, resistant bacteria equals to the new patient dot update So treated patient, update returns. Did it return a tuple? Oh, simulation with antibiotics here. Wait. Simulation with antibiotic returns. Oh, that's here. Okay, so then here, this gives us the number of bacteria with the update function. And then what we're going to call is resistant bacteria is equal to the new patient dot get resistance population. And what we're going to do is go total bacteria counts dot append the number of bacteria and the resistance bacteria counts dot append the resistant bacteria. Right, so that'll give us two lists of the total bacteria counts and the resistant bacteria counts. So then plot the average bacteria counts. Plot the average bacteria population size for both the total bacteria population and the plot the average bacteria population size for both the total bacteria population and the antibiotic resistance bacteria populations on the y-axis as a function of elapsed time on the same plot. You might find the helper function make two-plot curve helpful. This isn't my program. This is the MIT program, so they didn't provide me with any type-ins, unfortunately, which sucks. And I'm not really inclined to modify their stuff much. I don't want to mess too much stuff up, so I would if I was writing it from scratch, but it's not mine, unfortunately. Okay, so then we would need to just plot the average bacteria population size. What? Plot the average bacteria population size for both the total population and resistant population on the y-axis as a function of time. So if I have a list of these two, huh? Huh. What does it mean by the, so we'll say plot, make two plot curve, x coordinates are going to be the range of a list range of 400. Yeah. Then y coordinates 1 is going to be equal to the total bacteria counts. Y coordinates 2, resistance bacteria counts. Y name 1. Oh, total. Y name 2, resistant. And title with an antibiotic. Okay. So let's try this. Sorry, it's just an integer. Sorry, it's not a list. New patient, not okay. Untreated patient. Treated patient. Okay, let's try it. Patient missing. Line 770 is missing bacteria and max pop. $6.40. Okay, so now if we go try that one more time here. Jeez. Oh. 659, just fixing up some typos here. Resistant. Make 2 plot curves missing X label, Y label. X label, time step, Y label, average population. Okay. Okay, so our simulation with antibiotic function is something's wrong here. Um, so then we're going to say treat a patient, update, this gives us a number of bacteria, append that, and append. So if I print the length of total bacteria, let's print the length of resistant bacteria counts. $2,000, $20,000. Huh. Oh. Okay, so we get we're running a trial for the total bacteria counts and the resistance bacteria counts. So that's why they're here. Now what we're going to do is we're doing 100 trials, 50 trials. Right, so we're doing 50 trials. So this returns total population. So it returns a tuple of 2D lists. Okay, so then we're going to have bacteria counts and resistance counts. We'll have total. We'll have final. So list. We're going to have total, final. So then at the end of the simulation, we're going to append final bacterial counts dot append the average Is there a mean function? I thought there was. Population average. no. So we're going to take the sum of the total bacteria counts divided by the length of the bacterial counts. And then we're going to take this same thing, but do it via the resistant counts. This will be total resistant bacteria. So then this returns the list of lists in a tuple form. At each time step for each trial. Okay, so then we're just going to do this. Final bacterial counts, final resistant counts. We run. Oh gosh. That was bad. That was clearly not it. Dang it. Huh. What am I doing wrong here? It's already 10? It was just 9. Holy cow. Flying by. Okay, so we're going to run simulations and plot the graphs for problem 4. For each number of trial, instantiate a list of resistant bacteria. Right? Instantiate a patient. Run simulation 150 time steps. Add antibiotic. And run. Okay, oh, so what we're going to do is we're going to do. Oh, this is what. Okay, this will just. We do this. Sorry. Do this. Instead of this. This goes back. This is just patient. Patient. And then we call patient dot set antibiotic, and then we run for 250 more steps and then plot. Resistant bacteria on line 690. 770, 690. Resistant. Oh, there we go. That looks better. but it's not quite what we're looking for. Okay, so for every trial, we're going over trials, we're creating a list bacteria count. So this has how many trials? 50 trials. Okay, so what we're going to do is go over 50 loops. So there'll be 50 values into here, and 50 values into here. For 50 lists. A tuple of two lists or 2D arrays, the total number of bacteria at each time step for each trial. So I don't think I want to be doing this averaging thing. So let's just append total bacteria counts and resistant bacteria counts. We get this. So that looks a lot better in relation to this graph here, but it's not going all the way down to the 100. So I think we need to add in a reference point as our initial, right? So we need to add in our initial counts, right? So if we do a list of 100 initial bacteria and a list of 0 resistant bacteria initially, and run that. No. So that's going to add in a list of values. We're going to append the value. Oh, so let's add in 100 and 0 here to start. No. Final bacteria counts as 100. Resistant counts as 0. We go through the trials. We instantiate a list. We then append the average total bacteria counts. Okay, hold on. So we add the number of bacteria and the number of resistant bacteria over each run. And I'm going to average this list Okay, so we would do the average of our current trial run. We're going to add that to the final bacteria counts. Oh my god. For every trial, the number of trials, turn it to two lists of, or 2D array of populations. A list of is the total number of bacteria at each trial. Is the total populations for trial I at time step j. Okay, so we have trial back. So we'll say trial bacterial counts and trial resistance counts. Resistant counts. We're then going to append the number of bacteria and the number population. Right, we'll get that and we'll append it. And we'll set the update, the antibiotic, call update to this, call number of resistant bacteria. So we're going to go like this. Get rid of this. So we're going to update the bacteria. Go here. And then off. Now this equals final bacteria. There's 0 in my Y. What? Oh my god. Okay, we have a list. We're going over every trial. We're creating the trial counts for the bacteria and resistance. There should be 150 data points that we're adding onto this one. Right? And we're adding 150 data points into this list. I think I know what we need to do. We need to go get the average. We need to get the average. So right now we have a list of all of the lists of time trials. I gotta come back to this tomorrow. I'm too tired. I'm beat, you guys. We're almost done though, but plot the average bacteria population size opposed to local bacterial. Returns a tuple of two lists of lists or 2D array populations. The total number of bacteria at each time step for each trial. Total population ij is the total population for trial I at time step j. So we have populations, resistant pop. For every trial, we're going to have the trial bacterial counts and then resistant counts. All right, we create a patient and we're going to go 150 times and update the patient 150 times. And append to the bacterial count 150 values and 150 values here. So now we have a list of 400 values. And so y coordinates 1 is that, y coordinates 2 is that. A list of data. So 50 trial runs with 150 data points. Okay, so then what we have to do, we have a list of lists. And so we need to plot the averages, right? So what we need to do is we need to take a y chords 1 is equal to a list, or we're going to say calculate population average. Population populations. We're going to calculate an average I for I in range hundred and fifty. Then we're going to come here and do y chords 2 is populations, resistant populations. I for every range in 250. Now if we plot these values, $390. Length of populations. Well, what's populations in this case? It's an empty list. Okay, so then at the end of every trial, we go populations dot append the trial bacterial counts, resistance population dot append trial resistant counts. Run that. So x coordinates so then what we're going to do is now we have 150 is within our x and our y. Our y shape. We need to add so it's 150 and 250. Let's just go 400 here. 400. That'll throw me an error though, I think. Oh no. Okay, now if we go here and add in a 100 and a 0 here and run. Trial index n int object not scriptable. For the population average. I'm calling this here in my y coords function, populations. So if I go make this a list, run. And okay, so then if I say y coords is 100 plus this, 0 plus this. Right, the y chord's 1 would be 100. 399. Right, so this is what we're getting here, which is close. But we need this to go to the 100, not to whatever this is. So the four hundred. So x coordinates will go to 401, and then we'll add in a value, a list of 100 here, plus this, a list of 0 here, plus this. There we go. I think that's it. How to make 0, 0 in the left corner. That probably is by default one. It is padded a little. Checking the code just make sure padding and margin. Plot dot tight layout. Should we add that to it? No, that didn't work. You set margins to 0. Oh, that worked. There we go. It was supposed to go all the way up to like 900 though. Huh. One. Huh. Okay, let's try the other plot then and see how that one looks. Hey Ethan, how's it going? Hey Overdue, how you doing? We're just chilling, trying to solve this one here. Oh, let's see, something's wrong. Something is wrong. Ugh, I don't know what's wrong. How can this one be so off? Oh, because I'm forcing this here, right? So I wonder, maybe our thing is just wrong here. There's 400 here. Right. So our average population is not being computed correctly. Right. Okay, so we're a little off here. But I gotta go to bed. I'm tired, you guys. Yeah, chat is dead. I'm dead too. It's my own fault. I'm on beat too, you guys. Um, so for every trial, we're going to create a resistant bacteria list. We're going to instantiate a patient and run 150 steps where we add and then add the antibiotic and then run another 250. We're going to record the total bacteria population and the resistance bacteria population after each step in the trial. We're going to plot the average bacteria population size for both bacteria population and the antibiotic resistance on the y-axis. As a function over the elapsed times, you might find the helper function helpful. Yeah, I don't know. All right, I'm gonna go call it here, you guys. I'll see you guys tomorrow. Well, we'll finish this up. I'm dead.